Yeah, so let's continue. So sorry for torturing you more, but right. So I would like today to discuss a little bit how this theorem looks like. What are the consequences? First of all, let's say t equal to S1, right? So then, what does the theorem say? So the integral with the Liouville form. Now mu again is just a function. Xi is just a number. So it's an exponential of xi times mu. So what is going to be on the right-hand side? So here all these products, they will be just products of numbers. So this is now an integer. This is some number, right? So this is just a product. So here all the linear functions, they will all just proportional to xi with different coefficients. So in total there will be xi which parameterize this t action. So in fact you can take now xi outside the sum because there will be kind of all these linear functions, they're all the same, just the coefficients are different. And here there will be some m in mt and exponential xi mu of m divided by the product of integers. So these are just weights of the S1 action. So that's actually already a very, very interesting inequality because the left-hand side is a nice smooth function in xi, and the right-hand side, a priori, it has a pole of order n. So it's 1 over xi over n, and then times some kind of smooth function. In particular, if we just look at the Taylor series of the left-hand side and of the right-hand side, we already can make the following observations. So for all, let's say, s from 0 to n minus 1, and I will just consider the coefficient in front of 1 over xi to the power n minus s. Right? So on the left-hand side, there is nothing, right? It's a smooth function. So it will be 0. But on the right-hand side, if I take a Taylor expansion for each of those exponential functions, right? So I'm going to find the following. So this will be sum over m in mt mu of m to the power s. And this is divided by product j and j of n. Right? So if I here take the Taylor series coefficient number s, so coefficient in front of xi to the power s in the Taylor expansion of the exponential function, this will be xi to the power s divided by xi to the power n, and it will be singular for all these values of s. So all these kind of Laurent, so these are coefficient in front of 1 over xi to the power n minus s. So these are all singularities of the right-hand side. And of course, all these coefficients, they have to vanish. Otherwise, the right-hand side can never be equal to the left-hand side. Right? So that's so all these funny equalities. So the values of our function mu of m at the fixed points, they have to satisfy all these equations. Otherwise, we can't have, so this formula cannot be valid. Another funny observation. Now suppose you take the zeros Taylor coefficient on the left-hand side, right? So when here we take exponential of xi mu and decompose it, and we take coefficient in front of xi to the power 0. What would it be? On the left-hand side, right? So this will be the symplectic volume of our manifold. And on the right-hand side, it will be a somewhat similar expression to this one, right? This will be 2 pi to the n over n factorial times sum n in mt mu of m to the power n divided by the product nj of m. So that's the first Taylor coefficient. Here, when we exactly cancel the singularity xi to the n, so we take the coefficient of degree n, and then that's what our localization formula gives us. So this is a volume of m omega, and somehow interestingly, it can be computed by sum of powers of the values of the moment map function divided by the products of weights. So that gives you this kind of interesting or surprising equalities. Perhaps let's look at how these equalities look like in some particularly simple case. So let's take M to be a two-sphere. Remember, sometimes we were taking it to be of radius r, and we're looking at the S1 action. So we can imagine we call it two-sphere in R3. So that's the S1 action, and the moment map for this S1 action is just a z coordinate. So the radius is r. So let's just write down the localization formula in this case. So here there will be omega to the power 1 divided by 1 factorial. So exponential xi mu will be equal to 2 pi over xi. Now, well, that's fortunately an example that we know well. So there are two fixed points, the north pole and the south pole. So here there will be exponential of xi times the value of the z coordinate at the north pole, which is r, divided by the weight. So the weight, it turns out, will be +1, and here at the south pole it's -r, and the weight, it turns out, will be -1. In fact, perhaps here one should give a remark. In fact, when I formulated the localization formula, there was a little bit of cheating that you haven't noticed. So I think there were some experts in the audience. Where was the cheating? Or I think, let's say it's incomplete. It's not cheating, but it's incomplete. The statement of the localization formula is incomplete. One needs to add something. Maybe I give you a hint. You know, I said that the left-hand side of the localization formula is very well defined. In the right-hand side, we're using weights. But the weights are not, the weights of a t action are not completely well defined. Because you can always, for instance, we're choosing some z coordinates, right? We're choosing those copies of c, and we're using z coordinates. But what if we use a z bar coordinate instead? right? So if you have a T action or S1 action, say, and then you replace Z with Z bar, then Z bar rotates in the opposite direction. So actually, the weights are well defined only up to a sign. You can always like choose whether you want a weight n or you want a weight minus n. That's somehow your choice. But then it's not so great for our formula because on the right-hand side we have a product of weights. For instance, here I said the weight turns out to be +1, the weight turns out to be -1. So nobody raised any question. But what does it mean it turns out? In view of what I just said, it's actually our choice to some extent. So this is not very good, right? Because then the signs of the terms on the right-hand side will not be well defined. What do you think can be the answer to it?
Can you introduce some almost complex structure?
Probably, yeah, that's one possibility, but maybe we just operate like an almost complex structure. That's a big gun. Let's try to. So in fact, you know, the sign of the weight is fixed once you choose an orientation, right? So once you've chosen an orientation, you know who is Z and who is Z bar, for instance, or what rotates positively and what rotates negatively, right? So recall, so there is this product of weights. Psi, right? Right? If we choose orientations on those copies of C, this would fix uniquely the signs of weights. So now we have all these choices of orientations. But notice that if we have orientations on all of our copies of C or on all of our copies of R2, so this will induce an orientation on TMM, right? But TMM is already oriented. So we want this orientation to coincide with the orientation of TMM, which is induced by the symplectic form. So we want it to coincide with the orientation defined by omega. Now, the particular weights are still not well defined because we can choose orientations as we want. But if we change orientation of one of those C's such that the sign of the weight changes, we have to change an orientation of another one such that the total orientation of this guy wouldn't change. And this means that those changes would always come in pairs. And of course, if you change two signs, it's not so bad. So the weights themselves, they're not well defined, but this product is well defined. In particular, when I say it turns out that this is +1 and this is -1, this means that the orientation of this tangent space defined by the symplectic form is such that here the rotation is positive and here the rotation is negative. Right? So that's the statement. All right. So if we come back to this formula, then so these two equations, how would they read? So this equation, now n is equal to 1, so there is only s equal to 0 statement. So, the first type of equation will read 0 is equal to mu of m at the north pole to the power 0, which means 1 divided by plus 1 plus, again, 1 divided by minus 1. And it looks like true, right? So plus 1 minus 1 is equal to 0. So that's this equation for s equal to 0. Now, what about this equation? How would it look like? So the volume of S2R omega will be equal to 2 pi to the power 1. And then here we have R divided by plus 1 plus minus R divided by minus 1. Right? So that's what we get. And this is equal to 4 pi R. And I think it coincides with the symplectic volume of the corresponding two sphere. I had one more example, but probably we don't have that much time. Let me finish with the proposition. So this proposition puts together this theorem about Dustermack-Heckman measures and the localization formula. So let's say S1 m omega mu m to R, a compact connected Hamiltonian S1 space, x in mu of m, irregular value such that S1 acts on mu minus 1 of x freely. So then there is a formula, interesting formula for the volume of mx. So a small combinatorial factor, so 2 pi to the power n minus 1 over n minus 1 factorial. And here's sum over m in mt such that mu of m is bigger than x. And here mu of m minus x to the power m minus 1 divided by the product of weights. Again, that's the simplest case of such a formula, but I think it it tells you that you can completely control, in this case, the information about quotients, for instance, such as those volume functions. In principle, one can do similar things for many other integrals or intersection pairings, but let's say we do it for volumes. And we have a formula completely in terms of a fixed point data, right? In terms of values of the moment map at the fixed points and of the weights of the S1 action on the tangent space at a fixed point. And here you see, like, somehow mysteriously, we only now take a sum over the fixed points where the value of the function is greater than x. There is a similar formula. You can rewrite it in terms of the other, the fixed points where mu of m is smaller than x. Well, so let's see why is this true? So why is this surprising formula true? So now we have to put everything together. And first thing, perhaps in the localization formula, localization formula was an equality of analytic functions. And since it's an equality of analytic functions, I perhaps prefer to replace my real argument by a pure imaginary argument. So in any event, it should be true for any complex numbers. So I would like to write my formula, so the localization formula in the following way. So yeah, so instead of psi, I write a pure imaginary argument. And well, this should be equal to pi over it to the power n, sum over fixed points so why not? So that's the localization formula. And I would like to rewrite the left-hand side as an integral over the real axis. Indeed, let's push forward everything here. So we already know that the push forward of the measure, just by definition, it's called the Dürr-Heckman measure of m. But this function, exponential of it mu, that's actually just a pullback under the moment map of the function exponential of itx. Because mu is equal to x, that's just what we do when we perform the push forward. Right, so in fact, this left-hand side is a kind of Fourier transform of the Dürr-Heckman measure. Right, now I would like to replace it with the following formula. So I replace my Dürr-Heckman measure by 2 pi times the volume function exponential of itx dx. Kind of, do I have a right to do it, or is it like a good idea? Maybe you should be a little bit worried because so this formula I proved for regular values, right? But in fact, so imagine that's my so my mu of m is a segment. So this is mu of m, and we know that there is a finite set of singular values, the images of the critical, of the connected components of the critical set of mu. So in fact, almost everywhere, our formula is fine. But then it's fine everywhere, right? Because we don't care so much of what happens in those finite number of points. Right. Okay. So now what I would like to do, I would like to take the inverse Fourier transform to to determine the volume function. Of course, the inverse Fourier transform, it works under some reasonable assumptions on what this function is, but this function is, as we know, piecewise polynomial, so on each of those segments it's polynomial, it's 0 outside this segment, so this function is sufficiently nice to apply the inverse Fourier transform. So this gives us, let me denote this integral I of t. So this will be something like this. 1 over 2 pi integral I of t exponential minus it x dt. Right. Very well. So now let's substitute, instead of I of t, let's substitute the localization, the right-hand side of the Dirichlet-Heckman formula. T exponential I C mu of m Yeah, so that's what we need to compute. Now, notice. So this, as I said, this I of t is a reasonably nice function, so this inverse Fourier transform is well defined. However, now we represent the I of t as a sum of relatively nasty contributions. So we cannot so easily exchange the sum, this finite sum with the integral, because once we take the sum apart, so the corresponding functions will have some poles, right? And these poles, they will we don't know what to do with them because they're exactly on the integration contour. Well, fortunately, in complex analysis, they teach us how to deal with such situations. So we now have, say, this is the T complex plane, and that's our integration. So our integration contour is just the real axis, and there is in each of these particular terms there is a huge singularity sitting at t equal to 0. So that's the t equal to 0 place. But in the total sum, in this I of t, as we know, this is a very nice analytic function, right? So there is no singularity at t equal to 0 at all. So this means that in principle, we can shift our integration contour here, either upwards or downwards or as we like, right? So let's, for instance, shift it downwards. Right? So we say that actually here, we shift the integration contour, and now we can take the sum apart, right? For this integral, now there is no longer singularity on the integration path. And each summand in the integral makes sense. So this is 1 over 2 pi times whatever 2 pi to the n, and now maybe over I, right? Over I. Sum mt 1 over product over j and j of m. And now an integral. So now we decided that's, for instance, this integral. And here what do I have? I have exponential it mu of m minus x divided by t to the power n dt. Right. But now this becomes an exercise, standard exercise from complex analysis, right? So those integrals we do know how to compute. I think, how is it? So if I'm not mistaken, if mu of m minus x greater than 0, then, so you correct me if I'm wrong, then I think you should close the contour in the upper half plane, and then the residue, the singularity will be inside the integration contour, and this means that this will give you what? This will give you I mu of m minus x to the power n minus 1. So that's the residue, right? Times 2 pi I. Could it be? Right? So that's divided by, yeah. Yeah, right. Right. Over n minus 1 factorial. Does it sound correct? So that's, and mu of m minus x smaller than 0. So then the integration contour closes in the lower half plane. There is no singularity at all, and one just gets 0. So that's surprisingly, that's like from the residue calculus, how we obtain those funny sums of fixed points where mu of m is greater than x. Of course, you see here we could have chosen a kind of, here it was just our choice. We could have chosen the contour to be in the upper half plane, and then of course it would be all the other way around. Then only the contributions for lower fixed points would have contributed. So now what does it give? It gives 1 over 2 pi over I to the power n. And here's some m in mt, but now mu of m greater than x. And here I to the power n minus 1. Mu of m minus x to the power n minus 1. 2 pi I. N minus 1 factorial. Product j and j of m, and hopefully now, so those 2 pi's cancel. I to the power n and I to the power n, they cancel, and what remains, I think, is what we promised. Yeah, so that's
Should we include the case when mu of m is equal to x, because it seems reasonable if n big is equal to 1.
Yeah, so that's a good question. Should we? What's your opinion? Should we include the case of mu of m equal to x? let's say, the answer is, well, you can try, but let's say this would be to a certain extent it would even be a research, not really a research project. But see, we don't include mu of m equal to x, because mu of m equal to x means what? This means that there are some fixed points in the fiber of x. Then for sure x is not a regular value. So then for instance, then the reduced space, it's not guaranteed it's even a manifold. Probably it's not a manifold. So and so on, right? Then at least you need to here we were saying we want to compute the what is its interpretation? What does it mean? So that would be kind of there. You are opening this Pandora box of studying some singular symplectic spaces. So the corresponding space is typically a singular symplectic space. So let me finish with the computation for the two-sphere, and maybe there would be occasion to again return to your question. So M is a two-sphere with the S1 action. So now let's see what. So what this formula gives. Of course, if we have x somewhere between r and minus r, there will be only one contribution now, right? So this will be contribution from the north pole. And here we have 2 pi to the power, sorry, I think, how is it? Is it to the power n or n minus 1? That confuses me a little bit. No, I think. I mean, you wrote on the statement of the proposition of n minus 1. N minus 1, I think. N minus 1, that would be more welcome. All right, so let's say, and yeah, sorry, there's this 2 pi I should find somewhere. So I think it's n minus 1. So 2 pi to the power 0 over 0 factorial, so this is 1. So there will be a contribution of the north pole, so in this sum. So this will be r minus x to the power n minus 1, which is 0, divided by the weight at the north pole, which is plus 1. And so this is equal to 1. And of course, this corresponds to the following fact. What's the reduced space at the regular level set? So the reduced space is a quotient of the level set. So the level set, so the fiber is just a circle, a parallel on our sphere, and divided by S1 is 1 point, right? So here mx is just equal to a point. So we're computing here the symplectic volume of that point, which is certainly not a very exciting thing, but it's a good news that it's equal to 1. Right. So certainly that's not the most exciting application of our theorem, but well, you see the formula does look beautiful, and yeah, that's a useful formula, an interesting formula where in closed form you kind of put together 2 big theorems. So one theorem on the properties of the DH measure, and the other theorem is localization formula. I think it was already kind of quite a long class today, so we stop here.